A safety instrumented system is not safe because the logic solver is certified. It is not safe because you have redundant transmitters. It is not safe because the shutdown valve is tagged as critical. It is not safe because the project has assigned a safety integrity level. And it is certainly not safe because the design package contains a polished SIL calculation. Functional safety begins somewhere far less comfortable. It begins with the hazard. What exactly can go wrong? How can it happen? How quickly can it escalate? What consequence follows? What protection already exists? What protection is genuinely independent? And how much additional risk reduction is actually required? That's where serious engineering begins. You are not designing a trip. You are designing a controlled response to a hazardous process condition. You are making a promise that when normal control fails, when an initiating event develops, and when the process begins moving toward danger, the safety instrumented function will detect the condition, decide correctly, and drive the plant toward a defined safe state within the available process safety time. That promise has to remain valid through design, construction, commissioning, operation, maintenance, modification, and eventual decommissioning. That is why functional safety is not a hardware problem. It is a life cycle problem. The first mistake many projects make is starting with SIL. Someone asks whether the function should be SIL1, SIL2, or SIL3 before the hazard event has even been properly defined. That reverses the engineering logic. The correct sequence is simple. Understand the hazard, understand the initiating causes, understand the consequence, understand the existing risk, define the tolerable risk, determine the necessary risk reduction, allocate that risk reduction across independent protection layers. Only then determine what the safety instrumented function must contribute. SIL is not the starting point. SIL is the result of the risk reduction argument. A high consequence does not automatically mean a high SIL. A low consequence does not automatically mean a low SIL. The required integrity depends on the combination of consequence, initiating frequency, and the legitimate risk reduction provided by other independent layers. That word, independent, is where many safety cases become weak. You may see a control loop, an alarm, and a shutdown function represented as 3 protection layers. But if all 3 use the same transmitter, the same impulse line, the same power supply, the same communication path, or the same final element, you may not have 3 layers. You may have one failure path presented in 3 different colors on a diagram. This is why system labels do not prove independence. Calling one function basic process control, another alarm protection, and another SIS does not automatically make them independent. You must examine the failure paths. Can the same failure create the demand and disable the protection? Can one utility failure defeat several layers? Can one incorrect calibration affect all channels? Can one blocked process connection blind multiple transmitters? Can one common software error propagate across supposedly redundant functions? If the answer is yes, the claim protection requires challenge. Redundancy is not independence. 2 transmitters are not automatically twice as safe as 1. 3 transmitters are not automatically safer than 2. If they share the same technology, environment, process connection, maintenance procedure, configuration error, or power source, the architecture may look robust while remaining vulnerable to common cause failure. Random hardware failure and systematic failure are different enemies. Random failures include transmitter faults, electronic component failures, solenoid failures, actuator faults, and valve sticking. These can often be modeled using failure data and managed through architecture, diagnostics, testing, repair, and redundancy. Systematic failures come from somewhere else. They come from wrong requirements, wrong set points, wrong voting logic, wrong valve action, wrong safe state definition, wrong assumptions, wrong software, wrong configuration, wrong maintenance procedures, wrong management decisions. You cannot calculate your way out of a wrong requirement. You cannot add another identical channel and expect it to correct the same incorrect design basis. That's why the safety life cycle matters. The life cycle is the real safety system. Hazard and risk assessment defines what needs protection. Allocation determines which protection layers carry which part of the risk reduction. The safety requirement specification converts the risk analysis into precise engineering requirements. Detailed engineering develops the sensor, logic, and final element architecture. Factory testing verifies the configured logic. Installation and commissioning establish the field implementation. Validation proves that the installed function performs the required safety action. Operations and maintenance preserve the required integrity. Management of change prevents later modifications from silently destroying the original safety basis. Every stage depends on the quality of the previous stage. A weak hazard analysis creates a weak requirement. A weak requirement creates a weak design. A weak design creates incomplete testing. Incomplete testing creates false confidence. And false confidence is one of the most dangerous outputs an engineering project can produce. The safety requirement specification is therefore not a documentation exercise. It is the contract between the hazard and the engineered response. For every safety instrumented function, you should be able to state exactly what hazardous event it addresses. You should know the initiating condition, the trip set point, the sensor arrangement, the voting logic, the required response time, the process safety time, the final elements, the safe state, the behavior on loss of power, the behavior on loss of instrument air, the fault response, the reset philosophy, the bypass rules, the proof test interval, the proof test coverage, the operating modes, the environmental conditions, the operator actions, the interfaces, the assumptions. If those requirements are vague, different disciplines will fill the gaps independently. Process engineering will assume one response time. Instrumentation will specify another. Mechanical engineering will select a valve with a different stroke time. Operations may later slow the movement to prevent process disturbance. The calculation will still show the original value. The plant will operate with a different reality. That is not an isolated discipline error. That is an interface failure. Functional safety is therefore an integration discipline. The sensor, logic solver, and final element form the visible chain, but the process dynamics decide whether the chain is effective. A trip set point is not just a number. The process continues to move after the trip condition is detected. There is sensor response time, signal transmission time, logic execution time, output actuation time, solenoid response, actuator movement, valve travel, process deceleration, pressure accumulation, thermal inertia, reaction continuation. If the trip is set too close to the maximum safe process limit, the function may act exactly as designed and still act too late. Reliability does not compensate for poor process understanding. The process safety time must drive the required response. Do not begin with what the instrument system can conveniently achieve. Begin with what the process physically requires. Then engineer the system to meet that need. The final element is often where the real reliability problem sits. Engineering teams may spend weeks debating logic solver architecture while giving limited attention to the shutdown valve. But the final element has to move against real process pressure, real fouling, real corrosion, real friction, real utility conditions, and real maintenance history. A valve that strokes perfectly in a workshop may not close under process differential pressure. A valve that moves during a partial stroke test may not complete full travel. A solenoid may energize while the actuator still fails. A position indication may change while the process isolation remains ineffective. Proof testing must therefore challenge the actual dangerous failure modes. The purpose of a proof test is not to demonstrate that a test procedure can be completed. Its purpose is to reveal dangerous hidden failures that normal diagnostics cannot detect. If your probability calculation assumes high proof test coverage, but the field procedure only checks the logic and output signal, the model and the plant have separated. That separation is a safety failure. Proof test interval is also a design parameter. It should not be decided casually during maintenance planning after the architecture is frozen. If the required integrity depends on testing every 6 months, then operations must be capable of performing that test every 6 months. Can the function be tested online? Will it require bypassing? Can the final element be fully challenged? Will production pressure cause repeated postponement? Can the device be safely isolated? Can the test restore the function correctly? A design that depends on an operational regime the plant cannot realistically sustain is not a good design. The probability of failure on demand is a model. It is not permanent proof. The calculation depends on assumptions about failure rates, test intervals, test coverage, repair times, bypass duration, common cause failure, and demand frequency. When those assumptions change, the safety case changes. If annual proof testing becomes 18-month testing, performance changes. If repair takes weeks instead of hours, performance changes. If demand frequency doubles, performance changes. If a bypass remains active, performance changes. If a replacement device has different diagnostics, performance changes. This is why operations data must feed back into engineering. Demand rates matter. Proof test findings matter. Spurious trips matter. Detected failures matter. Bypass durations matter. Repair delays matter. A safety instrumented function that trips frequently is not simply proving that it works. It may be telling you that the process control system is weak, the process is unstable, the initiating event frequency was underestimated, or the SIS is being used as routine control. A safety function should not become the normal method of keeping the process inside its operating envelope. When it does, the original assumptions deserve review. Operator action also requires realism. An alarm and operator response can provide risk reduction, but a person is not a relay. Will the alarm be noticed? Will it be understood? Is the response obvious? Is there enough time? Is the operator already overloaded? Does the event occur during startup, shutdown, or emergency conditions? Can the action actually be completed? Has it been trained? Has it been tested? Idealized human reliability has no place in a serious risk assessment. Startups, shutdowns, maintenance, utility failures, manual control, commissioning, cleaning, purging, and abnormal lineups must also be considered. Many hazardous events do not occur during stable normal operation. They occur when the process configuration is changing and the workload is high. A safety function designed only around steady-state operation may be weakest when the plant is most vulnerable. Management of change is where many validated systems quietly lose their integrity. The plant capacity increases, a feed composition changes, a trip set point is raised, a valve is replaced, a transmitter range changes, a software timer is modified, a shutdown delay is added, a proof test interval is extended. A bypass becomes operational practice. Each change may look small. Together, they can destroy the original safety basis. Every safety-related change should ask the same questions. Has the hazard changed? Has the initiating frequency changed? Has the consequence changed? Has the process safety time changed? Has independence changed? Has the proof test effectiveness changed? Has the demand rate changed? Does the required integrity remain valid? A bypass must also be treated as a temporary change to the safety case. When you bypass a safety instrumented function, you remove or weaken a protection layer. Who authorized it? How long can it remain? What compensating measures apply? Who knows it is active? How is it communicated at shift change? How is restoration verified? A bypass that remains because everyone assumes someone else owns it is not a maintenance issue. It is a management failure. This is why competence and accountability matter. Who owns the hazard analysis? Who owns the SIL determination? Who owns the safety requirement specification? Who owns the valve performance? Who owns the proof test strategy? Who owns the bypass? Who owns the modification? Who owns lifecycle performance after handover? When responsibility is distributed without clear accountability, critical assumptions disappear between departments. The engineering manager cannot treat functional safety as one specialist package. It touches process design, piping and instrumentation diagrams, control architecture, electrical power, shutdown valves, vendor packages, software, construction, commissioning, operations and maintenance. Timing matters as much as technical detail. If the SIL assessment is completed after equipment purchase, the project is already constrained. If the safety requirement specification is issued after logic development, the sequence is wrong. If proof testing is discussed after startup, maintainability has already been compromised. The life cycle has to be integrated into the project plan from the beginning. And when an analysis produces many high-integrity functions, management should become uncomfortable. Not because high SIL is automatically wrong, but because repeated dependence on high-integrity active protection may indicate that the process remains poorly defended by inherent design and independent layers. Before adding more redundancy, ask whether the hazard can be reduced. Can inventory be reduced? Can operating pressure be lowered? Can the initiating cause be eliminated? Can passive protection be improved? Can mechanical design remove part of the burden? The strongest safety function is often the one you no longer need, because the hazard was engineered out. That is the raw truth behind functional safety. The safety instrumented system is not the safety PLC. It is not the transmitter. It is not the shutdown valve. It is not the SIL certificate. It is the complete chain of justified decisions connecting the hazard to the safe state. Hazard understood, risk evaluated, BOUT, protection layers challenged, required risk reduction allocated, safety function precisely specified, architecture engineered, integrity demonstrated, system validated, performance maintained, changes controlled. Break any one of those links and the SIL number may become decoration. So stop designing trips, start engineering risk reduction, ask harder questions, challenge convenient assumptions, demand genuine independence, design proof testing before freezing the architecture. Treat final elements as seriously as logic solvers. Use operating data to challenge the original model, and never allow documentation to become more credible than the actual plant. Share your experience in the comments. Where do you see the biggest weaknesses in real safety instrumented system projects? Is it SIL determination, protection layer independence, final element reliability, proof testing, bypass control, competence, management of change? Have you seen a sophisticated safety system weakened by one simple assumption? Have you challenged a SIL requirement because the process design needed improvement first? Your practical lessons matter, especially the lessons learned the hard way. Like this episode, share it with engineers working across process safety, instrumentation, control systems, mechanical engineering, operations, maintenance, and project management, and subscribe to the channel for more technically grounded discussions on engineering design, standards, project execution, and functional safety. Follow my LinkedIn newsletter for more simplified standards, engineering principles, failure analysis, and practical design guidance. And when you review your next safety instrumented function, do not begin by asking what SIL it carries. Begin by asking what hazard it must stop, and whether the complete system can still keep that promise when the plant is under its worst credible conditions.